Clubhouse will start making programs there. The one advantage of Clubhouse that it should be more interactive. That like when later we want to do Clubhouse events after our main event, because like Manoj is gonna talk about, he has to present, but you cannot present in Clubhouse, but you can exchange questions at the Clubhouse. So there's advantages and disadvantages. We're gonna combine that. Sorry that Clubhouse you cannot join if you don't have Apple product, but we believe in shortly they will bring it in the Android. And there's a huge data science community there as well. So hopefully Android will come soon. So I will make a short introduction. My name is Murat. I'm co-founder of Magnimind Academy, and we've been holding that meetup groups for the last 2 years. We are happy to say that we organized over 150 events in the last 2 years. A lot of talks and lectures, mini boot camps, a lot of free events. And we hosted more than 17,000 people into our events. I think it's good. It's good feeling. And especially during COVID, we increased the number of events. So we try to give good basic fundamentals of data science, increase the awareness on data science, make connection among people, and start to good collaborative projects. We've been organizing all this, and I'm happy that it goes well. And I myself have started 4 or 5 additional projects where I work at Stanford as well. I did start projects with the people that we hosted, and also people that came our audience. So I think it's a good environment, and we want to do more of these events, and we will do also more interactive events in future. You can network with your other fellow audience in some specific events. So I recommend to join our meetup groups if you haven't, because we also announce in other platforms. And also recommend to follow our YouTube channel, subscribe YouTube channel where we have our recorded events. And so we'll continue to post more events in upcoming. We are gonna post 4 or 5 new talks in next 2 months. Hope that will be beneficial. And yeah, I won't take longer. And today I will announce Manoj. Is it a good way to say it? Manoj or Manoj, you say?
Yeah, it's pronounced Manoj. Yeah.
Manoj. Okay, great. So we are hosting Manoj Agarwal today. He's the veteran of the Silicon Valley. He's a software architect in Einstein platform team at the Salesforce. I'm really curious about to learn that. He has almost 25 years experience in the industry, building distributed systems, public cloud services, and machine learning platforms. It's really hard to find that someone with that diverse background and talk about this distributed systems. I think it's a very privilege for us to listen to. Hello, Manoj, we are waiting you. We love to hear from you today.
All right, thank you, Murat, and thanks Magnimind to allow me to actually talk to this audience today. I'll share my screen. Give me a second. Can you see my screen now?
Yes, I see it.
Okay.
Yep.
Okay, perfect. So this presentation actually it's not that long. If I just talk to myself, I can probably finish it in 15 minutes. So I'm really hoping this to be a interactive dialogue. So we get to like interact with each other and have more of a dialogue than monologue. So first thing first, who I am and why am I here? As Murat introduced me, I'm an architect in the Einstein platform team at Salesforce. Here are a few ways to reach me, and I'll share this slide at the end also, so you don't have to hurry up and note down all this information. What are we doing here today? So we are going to be talking about some challenges around machine learning engineering. And one of the people that I follow and admire in this machine learning engineering space is Alexi. And he aptly tweeted earlier this year that machine learning engineering is 99% engineering and 1% machine learning. And that's exactly what we'll be talking about today. So, just a brief background. What exactly is Salesforce Einstein? If you are hearing that name first time, so Salesforce Einstein is actually a product of Salesforce. It provides AI capabilities for CRM. So Salesforce has multiple products in different areas. So they have a sales cloud, marketing cloud. There are a bunch of those kind of cloud products. And Einstein is the platform that empowers machine learning and AI in all of those products. So our vision is that we want to provide AI for everyone. You don't have to be a data scientist or a PhD to leverage machine learning or AI. Any like IT administrator should also be able to configure predictions and AI in their system. And today we power billions of predictions per day. To be exact, it's like somewhere between 2 to 3 billion per day. And this talk, of course, is not to sell you Salesforce Einstein. This is about sharing some of the learnings that we have by building this platform. We have been building this for more than 5 years. So, how do we serve that many predictions, and what kind of challenges do we see at that scale? This talk is about sharing all of those learnings. So, before I dive deep into the specific model serving challenge that this talk is about, I want to give you a big picture where in the machine learning platform, where in the machine learning arena this model serving fit. So, machine learning at a very high level, there are three major components: feature engineering, model training, and model serving, also known as inferencing. So, in case of feature engineering, so let's dive deep into each of these areas for a second. So in case of feature engineering, you have your data available in some data lake or in some database or in form of like some, I don't know, files in Hadoop file system or something like that. So you start with a problem, you start identifying what data you will need for that problem. So that's the data collection part. Then you, out of that data, you start figuring out what features would matter to you. So that is the cleaning, filtering, and normalization part. And then eventually, when you have the features, you validate your assumptions. And finally, you have the data that's ready to be consumed by a machine learning platform. So next step you do with that data is you train a model. And it's not just the data, you also need to figure out what kind of machine learning algorithm you want to use. Depending on the type of problem, there are different types of machine learning algorithms, right? I'm sure you know about that. And then you pick one or other ML framework, like if you want to use TensorFlow or scikit-learn or whatever. Then you basically using all that information, you train your model and you run validation on that model. If that model is predicting good enough, if the performance of the model is good, then you say my model is ready, and then you're ready to serve. If not, then you basically kind of iterate over it. This process, you maybe go back to data, procure more data, or clean up the data, or select the features in a different way, or you tweak your parameters that you give to the models, and you retrain. So this is an iterative process, just like the data cleaning, the data feature engineering was. Uh, so at the end of it, you will have a model or multiple models also, depending on the kind of training you're doing. So finally, when you have one or multiple models, now you're ready to serve the predictions. Typically, these models are hosted in the form of a web service. So there is a web service that's wrapping around the model, and a query comes in from your application. You take the data, you run, you evaluate the model. There might be some logic, there might be multiple models involved, and uh, at the end of it, you tell the prediction to the application. So that so this part where you already have the model and now you have to serve predictions, that part we are calling model serving, and that will be the focus of this talk. How do we serve um, like in the order of millions of these models at a low latency, while also squeezing the efficiency out of the system, out of the hardware? That's the core of this talk. So any questions so far? Let me take a look at the chat window if there is any. Oh, yeah, for some reason, actually, I'm not able to see the chat window. So if there is any question, just shout it out. Oh, here is the Q&A window. Okay. So let's move forward. So now we know where it fits. So let me actually also give you another background about this. How do we have those millions of models that I was talking about? So Salesforce has several hundred thousand customers, and each customer can define one or more predictions depending on how many Salesforce products they're using. So if you do the math, like one or more models per customers and hundreds of thousands of customers, uh, the number of models they easily reach in the tune of millions of models. And then for each application, for each customer, there are multiple versions of the models as well that we support. So another question that you might have is, why do we train separate model for different customer? That's because different customers have different kind of data, and we really cannot use one customer's data to provide benefit to other customer, because customers can be comparators as well. So we literally we have to keep the data and the models separate for each of the customers, and that's where the challenge of serving these millions of models comes in. And when you serve models, these models need to be loaded in memory to be served. And we possibly cannot keep all of these models in memory, because that will be very costly. And so we part of this solution is memory management. How do you serve most of the models from memory while keeping only the required number of models in memory? And if a model is not required, how do you aggressively unload the model from memory and optimize for the number of requests that you can serve from memory? So these are the very high level requirements of a model serving system. I mean, first thing first, it should be able to predict. It should be able to host a model and expose that as a web service. So there are, and then there are many machine learning frameworks that data scientists would like to use for a valid reason, for because every framework has different kind of capabilities, strengths and weaknesses. So these frameworks are like scikit-learn, AutoML, TensorFlow that I'm talking about. So a prediction service should be able to support multiple of these frameworks and multiple versions of these frameworks, because you cannot mandate all the data scientists, all the teams using your platform to be on the same version of the framework. Then next requirement is that you should be able to support multiple versions of the models themselves. So models are regularly retrained to take advantage of the newly available data. And each new training iteration, it produces a new model version. So to support things like the canary deployment, gradual rollouts, or A/B testing, prediction service actually needs to support multiple versions of each of these models. And also, as we discussed before, we need to serve hundreds of thousands of these models or millions of these models, and with as many as possible from memory. So that's the low latency part. So let's see one by one, how do we address these requirements in our solution? So at a very basic level, here we have a prediction service. We can host a model inside it in memory. Models are typically stored in a service called model store, which can be just a glorified S3 or some other object storage. So let's assume that models are stored in S3, and I have a service that that knows how to invoke a particular uh, ML framework, particular machine learning framework. Here I'm showing AutoML. It could be TensorFlow. It could be anything else. So, but only thing is that I have this exposed as a web service. So whenever the request comes in, I go and download the model from the model store. I load that model using this framework library, and then I call predict method, and using that, I am able to serve that model. So this uh, basic prediction service fulfills my requirement to be able to predict uh, for a given machine learning framework. So check on the first requirement. Now, how do you support multiple frameworks and versions of those frameworks? So for that, uh, we are going to add one more component to our design. Instead of just having these machine learning framework libraries, here now we have a router component. So this router component is going to determine based on the query, based on the customer, and based on the application that's calling it, uh, which kind of framework is that request intended for. And you can assume that these are all like maybe separate containers which are hosting the router component, or each of these separate machine learning frameworks. So the router component inspects the request, sends the request to the appropriate machine learning framework container, and that container works the same way as we were describing before. It would go and download the model from model store, load it in memory, and serve the request. So with this kind of a simple setup, you're able to serve multiple kinds of machine learning frameworks and models. And also, like this is the way actually a lot of different inferencing platforms work. Like Sheldon actually has like very high level architecture, something like this, and there are multiple others. So I see a couple of questions. How long between question and prediction? So Bill is asking how long does it take between making a query and the prediction? What's the latency of this prediction service? So it largely depends on the model and how long does the model take to predict. The like in our case, the latency of the introduced by this whole prediction service is like few tens of milliseconds, and that includes like making the routing decisions and forwarding the request to the appropriate model. And after that, it's up to the like depending on the how big the model is, how long does it take to load that from memory. Also, and we will talk about this in the later slides, we cache the model in memory. So only on the first request, we are having to pay the penalty of downloading the model from S3 from model store and loading it in memory. And any subsequent request, we are serving it from memory. Next question Bill had is, do you build your own server cluster or use the cloud? So we are hosted in multiple clouds. We are hosted in AWS, GCP, also Azure. But in each of these cloud platforms, we are actually building our own Kubernetes cluster. So this is all hosted in Kubernetes and it's cloud provider agnostic. So I love these questions. Please keep them coming. Otherwise, we'll wrap up this session soon if you don't ask those questions. So let me move forward. Now, the next requirement, if you remember, we also have to serve multiple versions of these frameworks. So like here I'm showing AutoML 1.1, AutoML 2.0. Similarly, there could be TensorFlow 2.2, 2.4, and PyTorch, similar kind of models, similar kind of versions that I might have to support. So for that, we can extend the same concept of router and these frameworks being hosted on separate containers, separate versions of these frameworks hosted on separate containers. And we can solve the problem exactly the same way that we solve the multiple framework problem. Now, going into a little more interesting stuff, how do we support multiple versions of each model? So for that, we added one more component called this version management service. So this version management service is responsible for keeping track of multiple versions of a given model. So I'm not showing the model training part here in this picture, but whenever the model is trained, it actually registers itself in the model store as well as it populates some metadata in the version management service. So every new version, whenever the model is retrained, that gets registered in the version management service. And version management service then become responsible for figuring out for a given request, what version of the model should this system be serving. So, I mean, ideally, as soon as the new version is available, that should be served to all the requests. But there could be more sophisticated needs, like, for example, we don't want to use the newly trained model for all the customers. Maybe we want to do some A/B testing, or maybe we want to do gradual rollouts. Maybe we want to just have a canary deployment first, and if that works well, then we want to gradually roll out to all the customers. So all of that responsibility is actually taken care by this version management service. So now the way this whole flow works is that query comes in, this router component, it goes to the version management service. It asks what is the model version that I should be using to serve this particular request. And basically it sends the request context, what is the customer and what's the application, all that. And then it router then after it knows which version of the model and also which framework and framework version that model is using, it can route the request to the appropriate container. And then again, the container works exactly the same way. So that's how, by introducing this version management service, we are able to serve multiple versions of the same model, and also support gradual deployments and canary deployments and A/B testing, all those kind of things. Now we are going into the kind of meat of this presentation. How do you serve all of this with low latency? So just like in any distributed system, whenever you have latency challenges, caching comes in picture. So we also cache aggressively. First thing first, this routing service interacts with version management. So instead of hitting that service on every request, we cache some of the responses from version management service. And here, as we saw before, that we are downloading model from S3 or from object storage. Instead of hitting that object storage for every request, we also cache that, and there are multiple layers of caches that we deploy. One is the file storage based cache. So it's a basically file storage volume that's get associated with multiple serving containers. And whenever you need a model, you'll go to go to the object storage and download that to the local file system. So now that model is available for you to load from the disk instead of going over the network. And then you load that model into memory. So this is the in-memory cache in each of these containers. And uh, with this, you can serve like as many models as you can load in memory. But because memory of a container is limited, you can only have a limited number of models in memory. So we have to aggressively evict models that are not being used. So that's what we do. And whenever, let's say, a model is unused for a while, we unload that from memory and load other models that are being used. And next time when the request comes in, we would load it from the file store if it's not in memory. So with this, we can serve a lot of requests from just in memory. You don't have to go to the object store for every request. Next is how do you effectively scale to support hundreds of thousands of these models? So for scaling, just like in any other distributed system, you would actually run each of the services, multiple instances of them behind a load balancer. So your service can linearly scale. Here you apply the same concept here too. So for each of the serving containers, each of the framework and their version, you run multiple instances of them, and that's behind a load balancer. Same thing you do with the routing service. So each of these services and serving containers, you can actually benchmark and figure out how many requests per second can they sustain. And then it's just a math. Based on that, you can figure out how many instances of each container you need. And that's how you kind of scale linearly by replicating. But there is another factor in scaling, which is basically scaling for the number of models that you're serving. So let's just take a look at one cluster instead of complicating this diagram a lot. I'm just focusing on this one serving cluster, and let's spread this out. So let's say there are three containers, and these three containers are serving some like certain number of models. One strategy could be that you have a load balancer that directs the traffic to each of these containers in round robin fashion. So what will end up happening is that when you receive requests will randomly go to one of these nodes, and that node will look in memory. If the model is there, it will serve from memory. If it's not there, then it will go out to file store or to the model store and load the model in memory. So eventually, all of these three boxes will end up loading the same model in memory, right? So that's like that's not the efficient use of memory, and also uh, that also means that there are at least three initial requests that will pay that penalty of loading model from the model store. That's also known as cold start penalty. So instead of like doing routing these requests in a round robin fashion, if we route them based on some kind of a consistent hash, or it's also known as sticky routing, then we can make sure that all the requests coming for a different for a particular tenant always go to a particular node or particular set of nodes. And then there is a good chance if all the requests for that model are coming to the same node, then there is a good chance that that model would be already there in the memory, and we can serve that model from the memory. So this is how we kind of shard the model. Based on a consistent hash, we route the request to a particular instance. And actually, it doesn't have to be one instance, it could be multiple instances. So this one set of containers are serving one set of requests, and the other set of containers are serving other set of requests. And they're all serving this one particular framework and its version. And that way we have, so this is, you can say one cluster. That way we can have one cluster per framework per version. So with this, this kind of solves most of our issues that we talked about in our requirements list. But at this level, there are other issues that also crop up. So like there is the problem of noisy neighbors and hotspots. So if let's say, so if I go back to this diagram, here this set of nodes are serving a particular set of customers, right? We are sharding the model, or we are actually creating a consistent hash based on the, let's say, based on the tenant, and particular set of tenants are always being served by this cluster of containers. So if one of those tenants is using the system very heavily while others are not, then that tenant that's using the system very heavily can compromise the experience of the other tenants. So that is the noisy neighbor problem. And same thing, if let's say one particular model is being used a lot, then basically that becomes a hotspot. While like let's say this particular shard maybe it's serving thousands of requests per second, but other shards are sitting idle because they happen to have less active tenants hosted on them. So so we have these two problems that crop up at that scale: noisy neighbor and hotspots. So how do we solve that? So let's spread out this whole container. There are these 9 nodes that we were talking about, and we were saying that top 3 are serving one particular shard of models, next 3 are serving the second shard, and next 3 are serving the third shard. Instead of using the consistent hashing technique that would actually enable that sharding, uh, if we use a technique called shuffle sharding, that actually distributes the models across this whole cluster of 9 nodes more randomly. And so shuffle sharding works differently than the consistent hashing. It actually spreads your models across the whole cluster, and it does it more randomly. So it reduces the chance of your model being hosted with the same set of tenants on all the nodes. So it might be the case that on this first node you have tenant 1 and tenant 2, while in this second node you have tenant 2 and tenant 3, and uh, so the chances of one node being shared by the same set of tenant, that actually reduces. If you want to learn more about shuffle sharding, there is a great paper in AWS Builder Library. If you search for that online, and you'll be able to discover that. So one downside of that shuffle sharding is that instead of just having a formula to figure out the hash and routing it to one of these clusters, now you have to keep a map of which tenant is hosted on what node. So and the router needs to look at basically consult that map to figure that out. So for that we use actually you can use any kind of configuration service. Could be Zookeeper. We use HashiCorp console, but there is nothing like that you cannot do with Zookeeper also, or any other config map service. So by using Shuffle Shard, now we are kind of minimizing the possibility of noisy neighbor, and having a hot. Actually, we haven't solved hotspot yet. So this is just to solve the noisy neighbor problem, and we are storing all that information in config map. Now, to solve the hotspot problem, what is the hotspot problem again? Hotspot problem is that one particular model is being used a lot. So let's say that model is hosted on first and second node. So these two nodes are heavily used, while other nodes are not used at all, maybe or very or used very seldomly. So what essentially to solve that problem, what we need to do is we need to scale the model based on how much it's being used. So if one particular model is being used heavily, then that needs to be actually scaled to, let's say, instead of two, maybe that needs to be replicated to 6 different nodes. So that we solved using this config map, the same solution. We get the metrics out of the system, or that metrics tell us how much is a particular model being used, how many requests per second are we getting for a given model, and based on this metrics, we can tweak this config map. We can actually specify a particular model, and we can say how, this model is being served at these many number of nodes. And then router can pick up that configuration and start routing the requests to that many number of nodes. So this way we are scaling for each model. And so if there is a heavily used model, that probably would be replicated on multiple nodes. But if there is a like not that heavy used model, very seldomly used model, that will be hosted maybe to 1 or 2 nodes only. So that's all we have to serve a large number of models, mostly from memory in a cost efficient way and with low latency. So with this solution, we are able to basically support all of these requirements. And if you go back to, let's say, the Salesforce product, and so that's how actually we integrate with multiple products, and we power billions of predictions per day using this architecture. And here is my contact information again. So if you didn't get to ask any question here in this forum here, you can reach out to me via email or LinkedIn or Twitter. Let me see if there are any questions that I haven't answered so far. So we have a couple of them. So Nirav asked, are the Kubernetes clusters auto-scaled, or what's utilized for node sizing? So yes, that's right. Kubernetes clusters are auto-scaled. So there are a few custom metrics that we are using to auto-scale the Kubernetes cluster. Kubernetes by default can auto-scale based on the system metrics like CPU usage and memory usage. But we also auto-scale based on the number of requests received. And also there are couple of levels of auto scaling that you have in the Kubernetes cluster. One is the scaling of the containers itself. So you can scale number of containers that you're running, or pods, actually what they call number of pods that you're running. And also you need to scale the underlying hardware, underlying nodes accordingly. So whenever your density of a node is actually increasing beyond a certain point, then we also auto scale the hardware cluster as well. Another question I have from Dave is, what's your opinion of using special purpose neural net accelerator rather than CPU or GPU for doing model serving? So I probably won't be able to answer this question because this is more machine learning centric. I'm a platform person, but I think it depends on the problem and the machine learning algorithm you're using. If the algorithm is able to basically support parallelism, then yeah, you could use GPU. And I don't know, the special purpose neural net accelerator, if your algorithm is able to like take advantage of that, yeah, I don't see a reason why you should not be using that. And I can follow up, Dave. If you send me an email, I'll find somebody who can answer your question better than I did. Yafim asked, are the models kept in memory in the compressed form and uncompressed on the fly when needed? So that's a very good idea. We currently we don't keep them in memory in the compressed form because uncompressing them would again take some latency. So we keep them in the uncompressed form. So a model, when it's in memory, it's ready to serve. And if a model is not being used for, currently our configuration is 1 hour. If it's not being used for 1 hour, then we just unload that model. But yeah, compressing could be one trade-off that we can have. Instead of unloading the model completely, we can probably keep it in compressed form and uncompress it whenever the request comes in. Next question is, who makes AutoML and Delta Flow? So AutoML is actually, it's not one particular library. AutoML is actually, there are many companies that are making AutoML libraries and platforms. So AutoML is more of a concept. It's like the idea is that there are like specialized frameworks, TensorFlow, scikit-learn, where a data scientist goes and creates a machine learning solution, and and every problem requires like careful feature engineering and then model training. The AutoML frameworks and libraries that many companies have built, the idea behind that is that uh, the platform should be able to automatically automate a lot of the work that data scientists do by hand. So what do I mean by that? Um, this AutoML framework should be able to figure out what are the most relevant features. It should be able to figure out how to deal with the missing data. It should be able to figure out how to scale the data automatically. So a lot of things that for which data scientists and machine learning scientists have to make manual decisions, AutoML frameworks automate um, all of that. And that automation works for majority of the applications. So hence the word this AutoML. But there are like different libraries that come under that umbrella of AutoML. Salesforce has a library called Transmogrify. That's their AutoML framework. Azure has one. There are a lot of others in the industry. Delta Flow. Uh, Actually, I'm not that familiar with that. But there are again a bunch of orchestration systems. Usually they end up with this suffix flow. So these orchestration systems or pipelines, uh, they they allow you to specify a training workflow or a serving workflow in some declarative format that you can run over and over. Dave asked another question: is your model serving only on CPUs currently and not GPUs? We actually have both kind of models, CPUs and GPU based. So depending on the framework cluster that we are creating, if the framework requires, if the framework can take advantage of GPUs, we actually spin that up on the GPU based cluster. If you must, another question, how does the size of a typical model, how is the size of a typical model in bytes? So it depends on the type of problem that we are solving. There are some models that are very small in size. So a lot of like classification models, binary classification, multi-class classification models, or linear regression kind of models, they are very small, sometimes in hundreds of KBs, but definitely less than 1 megabyte. But then there are other kind of models that are very heavy, that are huge in size. So those tend to be like recommendation system models, or applications that are doing multiple model inferencing, or applications that or algorithms that actually index a lot of data, like k nearest neighbor kind of models. So they tend to be very big in size. Typically, like they could go up to like 500 meg or even more, depending on the customer as well. Compared to the size of the data that has to be fetched from the feature store for each inference. Yeah, that's a very another interesting point. I haven't actually talked about this. So when the request comes in, there are often cases when you have to pre-process the request before you send it to the model, and fetching the data from feature store to enrich the request is one very typical pattern that you see. So uh, the data that you are fetching from feature store, it depends on your application first of all, but typically that data is not more than, let's say, a few hundred Ks of bytes. Typically it's in tens of bytes. You just like maybe you got the ID, but you want to put the details of a particular application or a particular record in order before you send it for inferencing. So yeah, the features, the data that you fetch from feature store is not like comparable to the size of the model. They are two different orthogonal things. Then Yafim said further, does the model really need to be cached, or we are latency bound when fetching the latest features, which may have been updated, for example, number of transactions in the last 10 seconds? So models do need to be cached. If we fetch the model always from the model store, then yeah, that incurs latency. If the model is big, that latency could be huge, could be in number of seconds. So we don't want to pay that penalty every time. Um, I don't know if I understand this last part of this question, number of transactions in last 10 seconds. Maybe Yasin, we can follow up offline. Uh, An anonymous attendee asked, what technologies are you using for load balancing? Is that handled via auto scaling, Kubernetes, or other technologies? So yeah, load balancing actually is provided by Kubernetes. We create a Kubernetes service, and underneath it uses, let's say, if we are in AWS, it uses AWS load balancer. And whenever cluster auto scales, it actually registers the new nodes with the load balancer. So there is nothing new there. This is typically how auto scaling works. Is the cost of each inference calculated? So cost of each inference is estimated, yes, and that's estimated in the beginning when we are doing capacity planning. As well as we keep validating those estimates as and when we need to readjust the cluster. Um, and this is one of the this cost is driven from the metrics. So initially we have some assumptions. Let's say that one particular inference is going to take that much amount of CPU, and the model is going to be of this average size. So it's going to cost this much in terms of memory. But as the model keeps changing, those estimates may not stay valid. So we keep track of those changes in the form of metrics. And whenever we see those metrics drifting apart from the initial estimation, we do and recalculate the cost. Oh, cool. There are a bunch of other questions. So next question, Dave's asking, what percentage of your predictions are from artificial neural network versus other types of machine learning models? So we have some deep learning based use cases like voice recognition, chatbots. So for that, we use neural networks. But I would say if I have to guesstimate what percentage, probably 20% of the cases are those deep learning based use cases. Most of our use cases are pretty simple machine learning use cases that just use CPUs, and most of them are just like either classification use cases or simple like linear regression kind of use cases. So say the icon you're showing for AutoML 1.1 and 2.0 look like Google icon. Are you using an AutoML from Google? So yeah, I mean, I kind of stole that icon from somewhere. We are not using AutoML from Google. We are using Transmogrify library, AutoML library that's from Salesforce. I could not find a logo for the Transmogrify library from Salesforce. But yeah, look up for that. That's a pretty nifty AutoML library. For the nodes that run, next question from Yafim, for the nodes that run model serving, could you give a rough idea of what percentage of CPU time is spent on the actual model inferencing versus the rest of the work? For example, is it 20% is spent on inferencing, and rest is data management and routing overhead, or something like something else? So this is again that it depends kind of an answer. uh, because the overhead time is almost constant for all kind of requests. You always have to, let's say, talk to the version management service. You also always have to route the request. So that overhead you always have to pay no matter what kind of model it is. But the model inferencing time, it varies a lot from model to model. Some models take only a couple of milliseconds to predict. Other model, because they only have to like run a formula. Other models, they might take hundreds or even thousands of milliseconds. So it's very hard to get the rough idea of the percentage of CPU time that's spent. But I can tell the overhead is less than 100 millisecond, and the model inferencing time that varies between tens of milliseconds to a few hundreds of milliseconds. So one more question. Did you see? Did you say you only use neural network for voice and chatbot? Yeah, those are our primary use cases for which we use neural network, voice and chatbots. Yeah. We also have some experimentation use cases that use that use based on that have models based on pictures and videos, but they're at the POC stage right now. Do any models use feedback as to the success of the prediction? That's a very good question. So models don't directly use feedback when they are inferencing, but we use feedback of the model inference system at many different places. So one, from the engineering perspective, one feedback that we use about the how many times a model is being used, we use that data to scale the model. And other thing, we also keep track of the model metrics, like what is the value of the predicted value of the prediction, and then we compare that with the actual value whenever the actual value becomes available, and that tells us how much model, how accurate is our model. And if that accuracy, let's say, degrades over time, then that information is it is used as a feedback to retrain the model. So yeah, that model feedback is used at multiple places. All right. So if you have any more questions, feel free to reach out to me, and I'm looking forward to connect to all of you. Yeah, thanks so much for giving me. Oh, there is one more question. What percentage of your predictions are from Python? Yeah, that's a very good question too. Roughly, I would say about 40% of our applications that use Python-based containers, and rest of them use Java-based containers. We have very small use case where we use C++-based containers, but mostly are running Python or Java-based frameworks. Cool. All right. Thank you so much. Murat, are you still here?
Yes, I'm here. You guys get a lot of questions.
Yeah, I'm really glad that at least somebody was listening. And yeah, I got to answer a lot of questions. And there were a couple of questions that I could not answer. And I promise that if they reach out to me using my email or any of the other means, I'll find the right person to answer those questions.
Sure. I mean, if you can answer all the questions, it's not good sign too. So that's great. Really appreciate your time. It's very good. People very actually they stay on the line till the end of the session.
Thank you.
Appreciate your time. Hope to see you in another event. Maybe we can organize also. We can organize a clubhouse with you.
Yeah, absolutely. Actually, one question that I missed. Somebody asked in the beginning, how do I start in ML ops? So there are a lot of great avenues where you can go and learn about ML ops. There is a great community. It's called, if you go online, they have a website with mlops.community, and they also have their own Slack channel. So I'll highly recommend to check that out. And of course, this particular uh, community also seems great, and they all seem to understand the same kind of challenges. And so yeah, this is all staying engaged with this community is also a great way.
Great. Yeah, this our group here, the specific topics, you get really good professionals. They know the topic. That's what I like about it.
Yeah.
And you can organize specific events later. So thank you for your time. Please, if anyone needs any question about us and our programs, you can reach us. If you want to also give a presentation, please also send me an email that what you want to talk about. We're gonna go through with our team, and then happy to host your presentation.
All right. Thank you. I'll do that. Yeah.
Great. Have a good day.
Thank you. Thank you, everyone.
Yeah, bye.